be the same. So you can leave if you were already here.
Then you can ask them questions.
All right. Okay. Let's see if you rehearsed. All right. So basically, let's start with the basics. How can gravitational waves help to probe the universe? And the main thing here is that the gravitational interaction is very weak. So if you compare the rate of the interaction with the Hubble rate, well, you find that the gravitational interaction is sort of decoupled in a cosmological sense from the universe, from the temperature, from the Planck temperature. So it is really, I mean, if you have this means that doesn't mean that you cannot produce gravitational waves, of course, but if you have a source of gravitational waves, then they basically propagate freely through the universe. Okay, so because of the weakness of the gravitational interaction, the universe is transparent to gravitational waves. And that's an extremely interesting property. Of course, it is the reason why it has been so difficult to detect them, because they interact very weakly. But it also means that you can use them to probe the early universe. Because if you have a source here in the very early universe, then basically the gravitational waves produced, they propagate freely, pretty much like the photons of the cosmic microwave background after recombination. Okay, and therefore they can bring direct information from the early universe. And as we will see, okay, nothing is certain there because it's physics beyond the standard model, but there are many proposals of phenomena that can produce a stochastic gravitational wave background, so sort of a fossil radiation, pretty much like the cosmic microwave background. And if we are able to detect this fossil radiation, then we can use it as a test of high energy phenomena going on in the very early universe. So that's extremely interesting in this respect, gravitational waves to probe the universe. As you will see in the lecture of Danny, of course, they can be used also to probe the late universe. And in that case, you use the gravitational emission from binaries, typically to probe, for example, the rate of the expansion that gives you information on the universe content. Okay, but this is going to be then this afternoon and tomorrow, I believe, with Danny. Okay, so in my case, what I will try to tell you, so we will start with the basics of the gravitational wave equation of motion in a Friedmann-Lemaitre-Robertson-Walker space-time and its relevant solutions, generic solutions. We will then see how to characterize a stochastic background from the early universe. We will also see why sources in the early universe give rise to what we call a stochastic gravitational wave background. We will also see what is and will be known on this signal that has been measured, probably not one from the early universe, but a stochastic background has been measured, as you know, by pulsar timing arrays. And so I will do some digression on the measurement of pulsar timing arrays that I mean, if you have already seen it in past lectures, you can stop me and I can pass to other things. Okay, so, but I have it in the lecture just in case. And then we'll close by giving a few examples of stochastic gravitational wave background sources in the early universe with characteristic solutions. Okay, so you have certainly seen last week that then a gravitational wave emerged naturally in general relativity as a causal theory of gravitation. Okay, and how do you do to express them? You take a background space-time metric. You probably have done it with Minkowski, probably last week. You define a small perturbation over this background metric. You insert it into Einstein equations, and then if you are able to solve all the gauge issues that I'm sure you have seen last week, which I mean took probably 50 years to definitely solve historically, so it's not something far from being trivial. then you find a dynamical solution for the perturbation, which is propagating as a wave, and therefore you have demonstrated that the theory admits gravitational waves. So in the cosmological context, this scheme is performed, of course, starting from the Friedman metric, in which you have here the scale factor. And here I have inserted the perturbation tensor. Okay, so I'm neglecting scalar and vector perturbations. Okay, so you see that that would be the background metric, and this is the perturbation, which is then much smaller than 1 and transverse and traceless, superimposed on the homogeneous and isotropic background. And then you insert this perturb metric into the perturb-Einstein equation. So you have the background, which is basically the Friedman solution in which the universe expands, depending on the matter content of the background. So this can be radiation, matter, I mean, dark energy. I'm sure you know all this. And then there is here I'm stopping at first order, so the perturbation of the metric, and correspondingly the perturbation of the matter, of course. So when you done these 3 steps, here you get to step 4, find a dynamical solution. So first find the equation and a dynamical solution for the equation. So the equation is this one. Now this is the tensor perturbation. It is a wave equation with a friction term, which is given by the universe expansion. H is the Hubble rate. And what is the source? So the source is the tensor anisotropic stress. So it means, you see, the energy momentum tensor on the right side of Einstein equation must have a background perfect fluid component, okay, because it must be homogeneous and isotropic to satisfy the symmetries of the Friedman universe, okay. And then, as I told you, we go to first order, so we perturb this perfect fluid. And indeed, into this first order perturbation, you can decompose it into scalar vector and tensor components, like every 2-index tensor in the space-time. So you will have a part that this is the background pressure that goes here. You have a first perturbation in the metric, and then here you perturb the fluid, okay? And you have, of course, just a perturbation in the pressure. This is the shear. This is the bulk velocity. And then you have this part, which when you extract, actually this part, which is the transverse and traceless part, and it is indeed this part that you can have as a source of the correspondingly transverse and traceless perturbation, okay? So in the cosmological context, that's what we are going to look for in order to produce gravitational waves, some perturbation on top of the Friedman universe that has a transverse and traceless component. We will see examples. So there are no gravitational waves from the homogeneous matter component, okay? Now you might have seen maybe the fact that whenever you start to perturb something from a space-time, a background space-time which is curved, so not Minkowski, but whatever background space-time which is curved, it's very difficult to say what is a gravitational wave and what is the background perturbation. And you need to resort to a separation of scales, okay? So you can only define the waves if you have, so that the gravitational waves have a wavelength lambda, which is in general much smaller than the characteristic evolution of the background. Okay. Now, in cosmology, I just want to give this comment. The situation is somewhat different because the background has special symmetries, so it's homogeneous and isotropic. And in that sense, you can define a tensor mode also when its characteristic wavelength or scale of variation is of the same order of the background one, which in the Friedman-Roberts-Walker universe would be the Hubble, okay, the Hubble scale. And so we will see a typical example of this is inflation, for example. So you cannot say that these super horizon or horizon-like perturbations are indeed gravitational waves, because as we will see, they don't oscillate. but you can ascribe them to a tensor perturbation. Okay, so that's what differentiates really this way of tackling the problem to the one that we have seen, you probably have seen over Minkowski. Please.
Thank you. Yeah, just a question on this comment. So why can't we, is it just a terminology sort of point, as in like, why cannot I have a gravitational wave that first oscillates, then like freezes out, and then freezes back, gets back in, and then starts oscillating again?
We will see the solution. Okay. They don't oscillate over the horizon. We will see
the
but
like anything else. Well, that's the case for every particle, right? Or every...
Yeah, also the scalar mode, of course.
Okay.
Yes. Okay. Right, so now what one does, of course, in this case, you want to exploit the translational invariance and perform a Fourier transform in space. Mind that in the cosmological context, you don't transform Fourier transform in time, okay? Because time, you have no time reversal. Time flows only in one direction. So Fourier transform in time is in general not well defined, okay? So for now, we just Fourier transform in space. And this we can do because of the translational invariance. And so here we have then the modes of the tensor perturbation, plus and cross, as a function of time. And the same you do for the source. You have exactly the same expansion because they are both transverse and traceless. Okay. And then you can then substitute this expansion back into the equation, and you see that because of the linearity of the problem, we have stopped at first order in perturbation theory, in cosmological perturbation theory. The evolution equation decouples for each polarization mode. Okay, so this equation that here I've written with the generic ij index gets split into two equations. For the cross and plus polarization. Okay, where here now I have converted it to conformal time. So this is now the conformal Hubble factor, and this is now co-moving wave number, but it's the same equation. So you see here the Laplacian has become a k squared. Okay, and now let's see how we can solve this equation. Okay, in the trying to remain the most general possible. And we will see some sourced equation later on. But now I just want to give you a flavor of what we can do with this left-hand side. So we will put the source to 0, investigate the solution of the homogeneous equation in cosmologically relevant settings. So, as you know, in general, the scale factor is a power law. Okay, this power law can cover the epoch of matter domination. In this case, the n would be 2. Radiation domination, in this case, n equal 1. And the Sitter inflation, for which n is equal to -1, in terms of conformal time. Of course, the universe, the real scale factor smoothly transfers from inflation to radiation domination, to matter domination, and now to an accelerating universe with the domination of the cosmological constant. Okay, but if you want to really solve this equation, putting here the true solution for the scale factor, you need to do it numerically. Here we just sort of find different solutions for supposing that we are well in the matter era, or well in the domination era, or well during inflation. Okay. So the solution is simple, is in terms of spherical Bessel functions. And now this doesn't tell you much. This simply is telling you that is something that quite intuitively it is oscillating and decaying. Okay, decaying because of the expansion of the universe. So, but there are two notable limiting cases, which are sub-Hubble and super-Hubble modes, as we were saying. Okay. So to express these cases, you can actually define a new variable, which is just the scale factor times your perturbation. And in terms of this new variable, you can rewrite the equation in this way. You see, so there is no source. But now you have this time-dependent frequency. okay, where a double dot over A is nothing else but the Hubble factor squared. And so now you can study two solutions that are very relevant for the universe. The solution in which you are interested in wave numbers that are much larger than your Hubble factor, okay, so the case of sub-Hubble mode, k squared much larger than h squared, or the case of super Hubble modes in which the converse relation applies. Okay. So now, this case is absolutely trivial because you see, you eliminate this part and then you have just a wave equation, normal wave equation. So your solutions, now for H, so for big H, your solutions are just oscillating functions, and then you divide by A to get H. And so you have plane waves with some coefficient that you need, obviously, to set with the initial conditions. And the amplitude of the wave is decaying like 1 over A because the universe is expanding. So in this limit, for sub-Hubble modes, gravitational waves are plane waves with redshifting amplitude. Okay? And this is extremely relevant as this is going to describe the wave propagation after the source has stopped. Okay, so you imagine you have a source, the equation is different, then the source stops, and then the wave propagates as free waves, but redshifting. Now, what are the coefficients here that come from the initial conditions? So now if we suppose that we have a source that operates in a given time interval, eta final minus eta initial, okay, a time interval in the radiation-dominated era for simplicity, but one can do it in the matter era, there's no problem. Okay, in this case, of course, the solution before the source has stopped, you can use the green function method to solve it, okay, it's simple. And then you get some scale factor, of course the green function is just a sinus, and then you have the source here. Okay, and before the source has stopped. Then, once your source stops acting, what you need to do is you need to match this solution with the homogeneous one. And that will allow you to find the coefficient A and B. Okay. So the solution after the source has stopped for time larger than eta final is going to be plane waves. Okay, so I've just rewritten this. And then we will have these two coefficients that inherit the action of the source. And so these are just the integral of the green from eta in eta initial to eta final of the green functions times the source. Okay. Now let's see the other limit, which is super Hubble modes. Okay, in this case the solution is also extremely trivial, because basically you get rid of this term and there are no more oscillations. Okay? So a constant solves this equation. So in general you have a constant plus an integral of this sort, okay? But since A is growing, and typically during inflation when this solution is relevant, is growing very fast, then this is a decaying mode, okay? And in general it gets neglected. So basically here the full solution, you consider this as your initial condition, the constant, okay, at super horizon scale. So here what I'm showing is the HR normalized with this constant, okay, that I suppose comes from inflation, so it goes to 1, as a function of conformal time. And you see, so this is I have chosen here to plot this the particular wave number that enters the horizon at the moment of equality between matter and radiation. Okay, so k equality. So k squared equality is equal to h at equality, okay, at this particular moment. So for every time which is before the equality of matter and radiation, the solution is a constant. okay, that comes from inflation. And then when you get to the relevant time at which you enter the horizon, there you are, you get the other solution, this solution here, in which you have free oscillations decaying like 1 over A. Okay, so this is a typical behavior of cosmological gravitational waves coming from inflation. If it does not come from inflation, then you need to find another kind of initial condition that will depend on an active source. All right. So now, why this kind of sources give rise to a stochastic background? And what is a stochastic background? Okay, so a stochastic background is a signal for which only the statistical properties can be accessed. Okay, basically it is noise, and what you can access are, for example, its power spectral density. And the reason is because it is given by the incoherent superposition of sources that cannot be individually resolved. Okay, so from the LIGO website you have here an example of a stochastic background as a function of time, and you see it's basically just noise. So one example, very easy to understand, of this kind of signal is the superposition of deterministic gravitational wave signals, for which I mean binaries, basically. So from astrophysical binary source, deterministic because in that case you perfectly know the solution, right? You have seen I'm sure you have seen the waveform, so you know exactly what goes on with time. But if you have very many of them with too low signal-to-noise ratio, so that you cannot, for each of them, pick up the actual waveform, or maybe they overlap too much in time and frequency, then, you know, in this case, they give rise to a confusion noise. Okay, and pulsar timing array is exactly one example of these confusion noises we will see. On the other hand, in the early universe, the situation is a bit different. So the reason why you have a stochastic background is a bit different. It's not the superposition of very many or too many deterministic signals, but in some sense it is. But the point is, the point is that you have typically a source, because of course the conditions in the early universe, so the Friedman universe, has the same temperature, right, all over the place. So inflation is preparing your universe in a causal way. So you have the same characteristics regardless of your causal horizon, the same characteristic everywhere. So the source, which is driven by some physical phenomena that is causal, it's happening at the same time all over the universe. Okay? So the source is homogeneously and isotropically distributed, but it is correlated only on scales that are much smaller than the horizon at that particular time, and therefore much smaller than the detector resolution. We will see this now in detail. So this is the reason why gravitational waves in the early universe produce a stochastic background. Okay, so let's try to investigate this a bit more. So suppose we have a gravitational wave source that is acting at a given time t star in the early universe, okay? And now I'm not talking about inflation. I'm talking about a phase, for example, in which we have radiation domination. And therefore, there is associated a causal horizon, which is nothing else than the inverse Hubble factor at that particular time. Okay. Of course, a source that is operating at this time cannot produce a signal that is correlated on length or time scales that are larger than the causal horizon at that time, okay, because you can violate causality. So the characteristic length scale of the source, which is going to be associated to the typical size of variation of the tensor anisotropic stresses, okay, which is the source of gravitational waves, must satisfy this inequality. What does it mean? Now, today, okay, the source is long gone, right? But we access the gravitational wave signal in the form of these freely oscillating plane waves, okay, with some amplitude that depends on the source, as we have seen it. Of course, this particular characteristic size of the source, that is going to be the characteristic frequency of the signal, appears today on the sky with a given angular size, okay, which is just L star over the angular diameter distance. So today we, of course, our causal horizon is just the Hubble scale today, which is huge. And so we do access the signal from very many of these uncorrelated regions, okay? So they are correlated inside, the signal is correlated inside, but is uncorrelated outside because of this. So the number of uncorrelated regions that are accessible today, of course, is theta star to the minus 2. And now, if you suppose the typical angular resolution of a gravitational wave detector, 10 degrees, let's say, it means that basically you can resolve sources with angular correlation that corresponds to a redshift of 17. So it's really not the early universe. Typically, what are the angles at the early universe? As you probably know from CMB studies, you know, at the redshift of recombination, the angular size today of the horizon at recombination is about 1 degree. This is the first peak of the CMB spectrum. Now, we don't care really much about the CMB. We want stuff that occurred earlier, because I told you that that's the important point of gravitational waves, right? That you can access what happened earlier. And so let's take, for example, an interesting epoch, 100 GeV, okay, when the universe had a temperature of 100 GeV.
Should I start? Or just a quick question, sorry. This source here is after inflation but before recombination?
It did, yes.
And it cannot be before inflation because...
Before
then
inflation. Tell me what's there.
Okay.
Sorry, I know very little about cosmology. Why can you measure time with temperature?
Okay, at that point. So the thing is, yes, because the universe is in thermal equilibrium. Okay, so you assume that after inflation, okay, in which the universe was dominated by a scalar field, vacuum energy of a scalar field, this vacuum energy gets converted into thermal energy, okay? So the universe is in a thermal state of equilibrium, okay? And therefore, when basically you can, to the right-hand side of Einstein equation, you put a fluid, which is a radiation fluid in thermal equilibrium. That is, its energy density is characterized simply by its temperature. So rho goes like T to the 4th. Okay, there's no chalk. So it doesn't matter. So really the energy density goes like T to the 4th. And so you can establish then a one-to-one correspondence between the solution of the Einstein equation, or the Friedmann equation, which is the scale factor as a function of time, and the temperature that the fluid had at that time. Okay, we can see it later. Yeah. So it's true that cosmologists use different. In the late universe, they typically use redshift, which is just the ratio of the scale factor today. In the early universe, it's more common to measure time in terms of temperature because of this assumption of thermal equilibrium.
And maybe you're going to touch, maybe you're going to say it later, but what about the gravitational waves that come from inflation? These are not stochastic, right? They are background?
Are also stochastic for a different reason. Okay. Yeah, I think I have it later, yes. Okay, so, but now, let's take it just as a measurement of one epoch, okay? So now this is, I don't know.
electroweak scale?
It is the electroweak scale, but I wanted to tell him in seconds, maybe 10 to the minus 18 or something, seconds after the Big Bang or something like that. Would be a redshift of 10 to something, d8, no, more, 10 to the, okay, 10 to the 12, I don't know, I'm inventing numbers just to give you order of magnitude. So the angular size of this particular correlated region, suppose it's the same as the Hubble factor today, is 10 to the minus 12 degrees. So you see, your detector resolution is 10 degrees. So you see basically 10 to the 13 uncorrelated regions today. That's why it is a stochastic signal. You really cannot resolve each of these regions. Okay, so only the statistical properties of the signal can be accessed. Okay, so we have seen then we access today the gravitational signal from many independent horizon volumes, which means that Hij must be treated as a random variable, okay? You don't know the phases of this, you don't know its nature, you can treat it just as a random variable. And for example, what you want to see is the correlator of this random variable, okay? Where typically this thing would be an ensemble average, okay? You have a random variable and what you can do is study these properties as after you perform an ensemble average. Now, the point is, do we have an ensemble average in the universe? The intuitive answer is no, we have just one universe with one realization, right? So in principle, what do you do when you do this ensemble average over one realization? The truth is that what one does is an ergodic hypothesis, okay, which means that you say, okay, it's true, I have only one universe, I have had one source that operated at a temperature T star or a time T star as well, at the same time in the entire universe, okay? And I know that the correlation, the typical correlation of this process today is tiny. So I say, well, each of these things is an independent realization, so let's do, instead of an ensemble average, a volume average. Okay, so now, this guy here, you take it as an average over volume. Okay, and there you have your several realizations, and you can study the ensemble properties of your system. Now we will see this can also be interpreted as a time average, but is a bit more subtle. So for now, let's remain with the volume average. Okay, and then you also basically identify it with the average that I'm sure you have seen that is necessary to define the gravitational wave energy momentum tensor, right? Because you cannot define the energy momentum tensor of a gravitational wave in a particular space-time point, because of the equivalence principle, you can transfer to coordinates that are flat. So in order to get the energy density of a gravitational wave, you need to perform an average. And in a cosmological context, you identify this average with the volume 1 as well. Now, that's a notable exception, gravitational wave from inflation, as we said. There, all this does not apply. Why? Because you don't have this particular causal relation to satisfy, okay? But the point is that there, what is the source? The source are quantum fluctuations of the metric. And therefore, the randomness of the process comes from the intrinsic nature of the process, the fact that these are quantum fluctuations that become classical outside the horizon. Okay, so it is still a stochastic background. The reasons why it is a stochastic background are different. It's because of the quantum nature of the gravitational resourcing process. Okay, now what are then the characteristics of this correlator? In general, we assume that it is homogeneous and isotropic because the Friedman universe is, okay. Of course, these are conditions, so homogeneity is there. Isotropy, there can be induced anisotropy from the structure, from the matter structure today, okay, but at the level of the first level of this, we assume it is isotropic. It is unpolarized, okay, because in general, the parity symmetry is always respected in the universe because it is respected in the standard model, more or less, of particle physics. So we assume that if everything obeys the standard model, etc., we don't have parity violating sources. So the cross correlation between the plus polarization and the cross polarization is 0. Okay, or if you want to express it into helicity modes, you have the subtraction of the plus and minus, plus 2 and minus 2 modes, okay, which are in an helicity basis, is 0. So your signal does not violate helicity, of course, in a statistical sense. And then is Gaussian because of the central limit theorem, okay? So you access today the signal from a superposition of many independent regions, and therefore when you have many independent realizations of the process and you study its properties, you in general get a Gaussian behavior. Okay, and now with this simple situation, what does it mean? Basically, it means that the only thing you want to know, at least at the 0th order level, let's say, in the most simple situation, is the power spectrum. Okay, the power spectrum, because of Gaussianity, all the odd modes, when here you correlate 3, 5, etc., they are basically 0, or you report them to the power spectrum. Homogeneity and isotropy gives you the fact that the wave vectors are uncorrelated, so this is only 0 when k is equal to q. The unpolarized condition gives you that also you cannot cross-correlate different polarization, so plus and cross is 0, okay, so there is this delta. And then you have your power spectrum, okay. So Gaussian gives you that the two-point correlation function is enough to fully describe your signal. And now, what is this guy here? Well, you see, is the variance of the gravitational wave amplitude in real space. Okay, so you integrate, logarithmically integrate over all wave numbers. There is a Fourier transform here. You can do it easily. Okay, and so you understand that this quantity here is related to the energy density, of course, of the signal. Now, the point is, suppose now that this guy, the source is long gone, we want to access a process that operated in the early universe, so we have freely propagated subbubble modes, okay? And then this becomes very easy, okay? Because here, you multiply this guy with its complex conjugate, the oscillations go, right? And therefore, what you are left with in this correlation is basically 1 over a squared that comes from the square of this. And there, the only random part here comes from the source, of course, so these are these coefficients, and so the average only operates on the coefficients. Okay, so this is basically your HC, okay, in this particular context in which is the only one that is relevant. You know, you want to measure something today that operated in the early universe, and so you see that the characteristic strain goes like 1 over a to the 1 over a squared. And now let's exploit this thing here, and let's connect then to the gravitational wave energy density, okay? So you know this formula, this is the average. I was telling you before that you need, in order to define what is the energy density of a gravitational wave, here I go to conformal time, simply, from physical to conformal time, and then I define the power spectrum of the gravitational wave energy density per logarithmic unit of frequency. Okay, and then one says, okay, let's Fourier transform this guy. Let's assume that it satisfies the same properties of this one. I mean, it's just a time derivative, so there is no reason why it shouldn't. So it has the same properties, but now we have HC prime here. And now let's take the situation of freely propagating subbubble modes. Now, taking a time derivative here is completely trivial. You just get out a k and a minus k. And therefore, you get that this guy is simply k squared times the one that we had here. Okay, so the PSD, the power spectral density. Right, and now, there we go, the gravitational wave energy density per logarithmic unit of frequency becomes, you can do it, you need to Fourier transform, apply this into here, etc., and you get k squared hc, the power spectral density here of your tensor perturbation. Note that there is an a squared that comes because you go into conformal time, and therefore, the gravitational wave energy density goes like 1 over a to the fourth. Okay, so you fall again into places, everything is okay, gravitational wave energy density, this is radiation, okay, so it scales like radiation, 1 over a to the 4. For freely propagating subbubble modes, of course, not during the source. Okay, you need this to be really like radiation. So. Okay, so we have seen that the formalism is okay because we get this 1 over a to the 4. Now, I told you about Fourier transform in time. What happens? Okay, first of all, from this, you can simply rewrite things, and that's what you will see in papers. The gravitational wave energy density parameters today, eta 0 means today, okay, in which you basically divide by the critical energy density. You, in general, also express this 1 over a to the fourth behavior, okay, to transfer from the early epoch, star, eta star, to today. Okay, so it's basically this parameter. And now you want to make connection with the detection process. Okay, so the detection process is what? It is an interferometer today. You know that today you don't care about the expansion of the universe, right? I mean, if you measure over 10 years, like pulsar timing arrays have done, of course the universe does not, here on Earth does not appreciably expand over 2 years. So let's now get rid of all this business that we cannot Fourier transform in time, okay? Locally, you can, because you are actually accessing what? Freely propagating subbubble modes, okay? In which this is now basically a constant. It is the scale factor today, and now these are just already your Fourier transform. Okay, so it's very trivial. So you can Fourier transform in time as well. Okay, you fix the scale factor to the scale factor today. This is now the comoving wave number, but this is just the frequency. And therefore, you can make connection with what you see in all the papers about detection, which is a Fourier transform in time, and this is now a time average. Okay, and this is now the SH, so which is connected, so how is it called? It's not the power spectral density, but it is connected by factors of the frequency. And you can even, it is a power spectral density, you can even connect it with your omega. Okay, so everything is well behaved when you want to connect the early universe with what you can measure today under the hypothesis that I just detailed. Okay, now we go to observations. Is there any residual question? I have until?
12:15, a bit more, 12:20.
12:20. Okay. Maybe we postpone, if you don't mind. Okay. Now, what is or will be known about the stochastic background? Okay, so here, now you have this plot. We have omega gravitational waves as a function of frequency today. And there are all these colorful curves, which is what is known and will be known. So let's go one by one. First of all, you have some upper bounds. So you know that the gravitational wave energy today cannot overcome a given level. And this level is due to the fact that we have measured the isotropy and homogeneity of the universe. We have measured it thanks to the cosmic microwave background and Big Bang nucleosynthesis. Okay, so we know the level of anisotropy that is allowed. So how do we know it? We know it thanks to Friedman equation. Okay, so that's now I'm just rewriting Friedman equation in which the source is now, of course, the sum of all the energy density of all the things that are in the universe. So I sum the energy density, radiation, cold dark matter, baryons, whatever, and here I have also gravitational waves, if they are there. Okay, and of course, so gravitational waves influence how the universe expands. They go like radiation, so they are an extra radiation component. Now, the abundance of elements that are produced at Big Bang nucleosynthesis, they depend very sensitively on the expansion rate at Big Bang nucleosynthesis. Okay, so these abundances that we measure today that are coherent with what we get out of the theory of Big Bang nucleosynthesis tell us that this h of t, it is something at nucleosynthesis. It cannot be different. And therefore, the gravitational waves that are here, they cannot overcome a given bound. Cosmic microwave background, monopole, so not the anisotropies, just the monopole, is very similar. Okay, but it's just at a different temperature. So this is about 1 MeV, this is about 0.3 electron volt when we have CMB decoupling. Okay, and so these are bounds on the integrated gravitational wave energy density at or previously to Big Bang nucleosynthesis and to the CMB epochs. Okay, so it's really, you cannot have more energy than what these physical processes tell you, that are measurements. Okay, and that's why I plotted here independently on frequency, okay, because these are integrated bounds. Here, this one stops here and this one stops here, is not by chance, is because you integrate. So of course BBN tells you that you cannot have so-and-so gravitational waves before BBN, okay? So here you stop at a frequency which is the horizon at BBN, and this is the horizon at CMB. Okay, we have another observational bound, which is now CMB anisotropies. Okay, so not the monopole at 2.k Kelvin, but how the temperature fluctuates. And this is what has been measured, anisotropies and polarization, by Planck. So the Planck satellites, right, operated now on this kind of frequencies, okay, which are really the Hubble scale today and the Hubble scale at recombination. Because basically, what do these gravitational waves, if they are there? They do what is called integrated Sachs-Wolf effect. So they perturb the homogeneous universe, okay, to some level. Forget about this complicated equation, I don't have time. But basically, the concept is that you would expect some temperature anisotropies and some polarization in the CMB because of the presence of gravitational waves. Since you don't see it, you bound it. Okay, and here you have the CMB spectrum as a function of multiple. I'm sure you must have seen these kind of plots. And these are all measurements, okay? But these are measurements of, what is called the lensing signal. So it's something we expect from the late universe. In reality, the early universe signal would be this one, and we don't observe it. And because we don't observe it, we can put here these lines, which are the upper bound at CMB time. Okay, let's keep this. Now, other observational bounds are from the observatories that are operating today, Lago, Virgo, Cagra. Okay, I don't think I need to introduce, you all know, right? Yes. So you all know what I have measured as well, binaries. And this is from the latest paper, the constraints on the presence of a stochastic signal. All right, that could be from binaries, could be from something else. Of course, the bound does not assume any given source. It's just some reference amplitude at the reference frequency and with an open power law. Okay, and this is what the MCMC tells them. Basically, you get no bound on the spectral index, but you have an upper bound on the amplitude. Okay, and okay, so the bad news is that what you expect for present time interferometers on Earth is that when you get the best sensitivity ever, you will access the signal from astrophysical sources. Okay, so most probably there is going to be no detection of the stochastic signal from the early universe if it is there. At LVK, because it will be, whatever is there will be masked by the astrophysical sources. Okay.
So we can just...
So, right, and here one word, how do, so I told you that this signal is basically, is stochastic, and so it's basically noise. How do these detectors identify it? Is thanks to cross-correlation, because there are at least 3 detectors. Okay? Please go
sorry, very fast. Cosmological here is a sum of potentially inflationary early universe sources?
Yes, whatever can come from the early universe.
Okay.
Yeah, indeed. So yeah, so they cross-correlate, okay, the data stream from different detectors, and they say different detectors, they have independent noise, while the signal is there in all of them. Okay, so that's how they perform the measurement. Okay, then we have LISA here. So as well, I don't think I need to introduce, right? Is the future gravitational wave interferometer in space at much lower frequencies. I'm sure you have seen this. Is the target sources for the interferometer, and you see there is certainly one stochastic signal that we expect is all the noise from the galaxy, all the binaries in the galaxies, but there are many, at least proposals, also from the early universe. Okay, so what we expect in LISA? We expect the confusion noise from all the binaries in the galaxy, mainly white dwarf binaries. This is not too bad, okay? Of course, it affects the sensitivity of your detector, but because the detector goes around the sun, you see, it offers a different sensitivity that depends on the direction. So, as the sensitivity that depends on the direction changes because the detector is going round and round, you are more or less sensitive to this galactic signal, because the galaxy is only in one part of the sky. So depending on where you are on this orbit, you see it stronger or weaker. And therefore, it is a signal that is modulated in time. Over 1 year, it becomes maximal and goes back. So that's what could be used to sort of characterize this signal. On the other hand, everything that comes from extragalactic sources could be binaries outside of the galaxy, could be anything from the early universe, does not have this annual modulation. And we don't have 2 LISAs to cross-correlate, right? So here, really, with LISA, the problem is that whatever is a cosmological signal or astrophysical signal is exactly the same thing as noise. Okay, so you cannot cross-correlate, and if you want to perform a detection, you need somehow to assume, or to test that you know your noise. Okay. So here we see some example. I hope in this afternoon we will be able to characterize these signals, the different proposals. This is the galaxy, okay? This is extragalactic sources, and these are possible cosmological signals. So if we are lucky, so this is also a possible cosmological signal. So this is variably visible. But if we are lucky or unlucky, and that's what is there, then of course you don't need to worry a lot about the noise. I mean, this is a signal to noise ratio of whatever, 10 to the 4, so you see it. Okay, so that's the situation for LISA. So the main message is you cannot cross-correlate, and so detection is challenging unless you are in a situation with a huge signal. And now let's go to PTA, which is the first gravitational wave detection, right? Now, of course, yes, I also think I don't need to introduce here. You all know what pulsar timing arrays are. And now I have a few slides on what is the principle of the measurements, because I find that in the literature there is a bit of misleading statements. Do you want me to go through, or you know? You want me to go through? Okay. So now the principle of the measurement is gravitational redshift. Okay. And this gravitational redshift is caused by the gravitational waves emitted by a faraway source. Okay, so let's take here a supermassive black hole binary with some axis. Here we have Earth, here we have the pulsar. Okay, so this guy is emitting gravitational waves. They are traveling through space-time between the pulsar and the Earth. So what happens? Here you have this geodesic. So there is the pulsar is emitting a pulse, radio pulse at emission time TE. On Earth, we are receiving this radio signal at arrival time TA. The geodesic, if there was no gravitational waves, would be just a geodesic in the space-time due to all the gravitational sources that are between the pulsar and us. But we want to access the fact that the space-time is perturbed by the presence of the gravitational waves. So let's write the dt of the photon this way. Okay, so we have flat space-time. We don't care, of course, about the universe expansion because these pulsars are in the galaxy. There is the gravitational wave. And now, so the time difference between the emission and the arrival is just the distance between the pulsar and the Earth at first level. And then we have the perturbation. So this is the delta Ij. And then there is the perturbation. So you integrate over the affine parameter of the geodesic between us and the pulsar at emission time plus S and position of the pulsar RE plus S, U being the vector between the pulsar and us. Okay, of course, what is the problem is that in the literature you find, yes, it's due to the gravitational redshift. Here, you cannot measure anything, you agree? Unless you know L and you know TE, right? You cannot access Hij. So how do you access Hij? You access it because you have a second pulse, at least a second pulse. Okay, so the next pulse is emitted at T plus P and is received at TA plus P plus delta T. So P is the period of the pulsar. Okay, and now you want to know delta T. And so you actually now have the subtraction of, the first pulse, the geodesic of the first pulse, and the geodesic of the second pulse. And now you see you have here an effect, so this guy is different from zero only because the gravitational wave depends on time. Right? Because if you were just for the space part, the space part is the same. So it's really not gravitational redshift in the strict sense that you can consider from whatever, the sun and a background star. Really what has been here is really because you are accessing a wave that depends on time and you are comparing two separate pulses. Now here I just do a change of variable, okay? I just say, okay, this is now a plane wave. Why not? We are far away from the supermassive black hole, so I write it like this. I change the variable, okay? And of course now this is the wave at this variable plus p minus the wave at this variable. And there comes the point. The point why there is confusion in the literature is the fact that now, and I will tell you why, this guy is very close to this one. You Taylor expand, and when you Taylor expand, you do fall back into the usual gravitational redshift formula. Anyway, so let's go with order. So what do you do here? Let's say, okay, what is this Hij? Supposing that the source is the inspiral of a supermassive black hole binary. Now, you have seen this formula, I'm sure. That's the frequency as a function of the time to coalescence. Okay, we have the Chirp mass to the 5/8, time to coalescence to the 3/8. If we insert, for example, a Chirp mass of 10 to the 9 solar masses for a time of to coalescence of 10 to the 4 years, you get to the 10 to the minus 8 Hertz. Okay, and so 10 to the minus 8 Hertz is about 3 years. So you are now comparing your gravitational wave at a time x plus p, where this is a millisecond, because the period of the pulsar is millisecond, with the one at time t. And this guy varies on a characteristic scale of about 3 years. So you see, it's obvious that here you can Taylor expand, because the increment is tiny with respect to the variation of the function. And so in the end, if you now then divide by p after your Taylor expansion, you get what you're interested in. So the relative change in the rate of the pulses, which you measure, okay, because of the gravitational wave passing by. So you have this geometrical factor, and here is what is called the Earth term, okay, is Hij at the Earth position, this one, minus the pulsar term, Hij at the pulsar position. Okay, and this I already said, this is the change in frequency of the pulses due to the gravitational waves calculated between two successive geodesic, not the redshift experienced by one photon or on one geodesic, because that you cannot access. Okay, but the two expressions become the same in the limit of infinitesimal period of the pulsar, which is certainly a good limit given what you are interested in detecting. Okay, and now let's see the magic of pulsar timing arrays, right? What happens? Now you have this formula, and you say, okay, what is the typical signal, okay, that we want to access? So let's put here again Hij from a supermassive black hole binary of 10 to the 9 solar masses. We have seen it emits at a frequency of about 10 to the minus 8 Hertz. It scales like 1 over the luminosity distance. Okay, and you get that this is a number. Okay, is a time over time. And there you get 10 to the minus 16, more or less, 10 to the minus 17. Okay, from this thing. And now, what you say, okay, that's too small. Let me integrate it. Okay, so you are interested in the timing residuals, which is the integral over time of this guy from a reference time to some t. Okay. What is this t? Well, this t must be long enough for you to access the effect of your gravitational wave. So let's take it of about 3 years. Okay, which is what you are interested in accessing. And there you go, you integrate over 3 years something which is 7 times 10 to the minus 16, and you get about 60 nanoseconds. which is exactly the precision with which you can time these pulsars. So it is really the precision of your measurement that is telling you, look, with this precision, it's magic, we can actually access precisely this kind of sources. Okay, if you had a much smaller precision here, a much better precision, you could access sources with a smaller mass. Right. Okay, yeah. And so you see here the simulated data that over some 3 years period, right, you have this modulation and you can access it because here you have a, okay, that's over a microsecond, but you can actually access this kind of variation here over 100 nanoseconds. Right. Okay, now this is all very beautiful, but it's all very theoretical, because the reality is that this signal is extremely noisy, okay? So you see here this coincidence of numbers, very small numbers, you integrate, I mean, it's not... so in reality, you know, you have so many sources of noise that you need to do something more. And what is this something more is that you use many pulsars, okay? Why? Because, of course, all the sources of noises that are intrinsic to the pulsar, it is a very stable clock, but it can have, you know, changes in the time interval between the pulses. And then you have all the noise that is due to the propagation of the radio pulse through the interstellar medium from the pulsar to the Earth. You, of course, have the errors that are due to the fact that you need to know time very precisely, not only on Earth, but also in the solar system barycenter. So basically what you do is that you cross-correlate, because the gravitational wave is one, right? It's the same in the entire galaxy. The noise of the pulsars, if you change pulsar, they change. So you intuitively understand that if I cross-correlate the signal exactly like LVK of many different detectors, I access what is common. And I beat down the noise that is not common. Okay, now, of course, here is a bit more complicated. Here the point is that what is really, when you cross-correlate, what stands out, of course, is the Earth term. Because the Earth term is the gravitational wave that left the source at this time. The pulsar term is the gravitational wave that left the source at this time, okay? So the pulsar term is the gravitational wave at the pulsar space-time position. The Earth term is the one at the Earth space-time position. So when you cross-correlate different pulsar, this term is different. So in the cross-correlation, it goes away, and you only remain with the one of the Earth, okay? That's true for a stochastic signal, not if you access the signal of just one source, but I'm not considering this. Okay, and now let's see this in practice. So you want to cross-correlate the response of a pair of pulsars to a stochastic background. Okay, so you cross-correlate over time this guy here. This guy here, you basically now get these two terms, and you write this as a plane wave. Okay, so that's your plane wave. Here I taken out this part. Okay, and this is basically this angular factor that, of course, depends on the pulsar. It depends on you. So you have it here for pulsar A. Okay, so pulsar A, pulsar B. And then when you cross-correlate this famous average that we have been, transferring from gravitational waves to the early universe to an ergodic theory in two volume, here again becomes the average that defines your power spectrum. Okay, everything is more or less well behaved in this simple case. And now here you see that this particular term here, that appears twice, okay, because I'm cross-correlating, is where you see the pulsar term disappearing. So this is the pulsar term. This is the Earth term, as I have rewritten it, okay? And now these oscillations here, they oscillate like crazy, because this is basically 10 to the minus 8 Hertz is K of your wave. But LA is about 500 parsec, is the distance between the Earth of the and the pulsar. So you have that this guy is about 3,000, and so these oscillatory terms are utterly negligible unless you consider the same pulsar, in which case they go away, or unless you are really, the pulsar is aligned with the source. But I mean, in all practical purposes, this goes to 1, and so you access the Earth term. And then there is this calculation that no one does. I've never seen it, and I haven't done it either, which is the famous Hellingsdown curve. So from the integral of these geometrical factors, you get a characteristic response as a function of the angle between two pulsars, okay, which has this form. And all the rest becomes just your signal. Hc is the power spectral density of the signal. Okay? Yeah? Okay, and now I have all the digression on supermassive black hole binaries, but I assume you have done it with Alberto. Yeah? Yeah. Because, as you know, pulsar timing arrays, as I have been saying, they measure supermassive black hole binaries. And so there is an entire problem of how do these supermassive black hole binaries form. Because we see them in the X-ray when they have a separation of about a kiloparsec, but in order to emit gravitational waves, they need to go to the milliparsec separation, okay, the two black holes. And basically this observation of pulsar timing arrays, which is probably then the background from supermassive black hole binaries, means that they exist and merge in the universe. Okay, I need to speed up, so here I have a calculation of why this particular signal that they measure goes like f to the 2/3. Do you do it, Alberto, in your... No. Do you want to know? Because there is a lot, I have other stuff to tell you, going back to the early universe. Maybe you prefer to go back to the early universe? Yeah. Yeah, very good. Okay, so here is all the pulsar detection, and finally, so I say here, you see, there are some tensions that are probably now solved, but in some sense, you have predictions from this stochastic background from the supermassive black hole binaries. You have predictions that somehow vary on, how you model the astrophysical sources, and these predictions are maybe a bit in tension with what is measured. Okay, I'm pretty sure that this will be resolved, but one can also say, okay, but maybe this tension is because what you see is not only or not exclusively supermassive black hole binaries, but there is something that comes from the early universe. Let's investigate this possibility. Okay, so now what happens? Examples of stochastic background sources in the early universe. Okay, so here we have this cartoon. There is the history of the universe. Don't believe this thing. I don't know why they have this thing, but what we know is that we have inflation, which is a phase of accelerated expansion, and then we go ahead with the power law expansions, radiation, and matter, and then lately, now we also probably go back to some accelerated expansion with dark energy. And here you have all the phases okay, of what happens to this plasma in thermal equilibrium. Okay. So, what have we tested in cosmology? We have seen the cosmic microwave background at about 0.3 electron volt, but we have actually tested even more because of Big Bang nucleosynthesis, as I told you. So, tested cosmology is basically from 0.1 MeV to lower temperatures we are today now. Of course, through the CMB anisotropies, we also access the physics of inflation. Okay. But all this part here, photons are tightly coupled, and so we cannot access all this part with electromagnetic radiation. Physics has been tested until about TeV. This is what has been tested at the Large Hadron Collider. And so there is a frontier here in which when the universe had temperature basically higher than 1 TeV, we don't know what is the physics there that describes the status of the universe. Okay. So we have two frontiers, tested cosmology and tested physics. Okay. And now we want to use, as I told you, gravitational waves to try to access typically this new physics region. Okay. So in a complementary way to colliders. And there are, of course, there is nothing you can say with precision here because this is new physics, so you have no idea what is the fundamental theory that describes the universe here. So from here down is the standard model of particle physics, but before you don't know. But you can speculate. And in general, to produce gravitational waves, one needs to have phase transitions. We will see why in the afternoon. What is a phase transition? Is a phenomenon in which there is some field, okay, that changes from one state to the other. For example, the Higgs field. And why there is this change is because the temperature is decreasing, and therefore the new state has become more energetically favorable, okay, due to this change in external conditions. So the change in temperature due to the expansion of the universe. Now, the first phase transition that we have is inflation, that, as I said, we access through CMB anisotropies. Okay, inflation is the phase transition of the inflaton field that goes from a state in which it is dominated by vacuum energy to a state in which instead it goes to the actual zero of the field potential. And by doing so, it transfers all its energy into thermal radiation particles, standard model, or maybe not standard model, but particles. Okay. The other phase transition that we have is a grand unified theory phase transition, okay? So here you say, here there is no standard model. The symmetries of the standard model must arise from this theory that has higher kind of symmetries. And these symmetries, of course, they must be broken, because today we have the standard model, and this breaking of these symmetries correspond to phase transitions, spontaneous phase transitions that can maybe produce gravitational waves. One of these phase transitions is required to solve the strong CP problem. So why the strong interaction does not violate CP? Okay, that's the standard model tells you that it should. There is an operator for which you should see CP violation. You don't see it, and so Pecci and Quinn have made the hypothesis that there is this phase transition in which you actually get rid of this CP violating operator. Okay, and this happens at this kind of temperature, 10 to the 7, 10 to 11 GeV. We will see that this is measurable by LIGO-Virgo-Kagra, if it is there. We have then the electroweak scale, which is the barrier, the frontier between new physics and tested physics. Okay, this is the phase transition of the Higgs field, in which you basically separate the weak and the electromagnetic force. Okay, so this is also extremely interesting, and it is in the frequency range of LISA. And then we have the QCD phase transition. This is in principle in the realm of tested physics, but it is extremely difficult because the stronger interaction is stronger, so it is non-perturbative, so it's difficult to analyze. Okay, but we know that there has been this phase transition in which you have confined hadrons, quarks into hadrons, so the formation of the proton, the neutron, etc. This happened at 0.1 GeV, and it is the energy testable by pulsar timing arrays. So you see, we have three motivated phase transition in the early universe. We don't know, I mean, at least the QCD and the electroweak one, we know they are there. They can be tested by pulsar timing arrays, LISA, and then we have the Patrick Queen one, which is in the scale of LIGO Virgo Cagra. And why? Because when you go down in temperature, or let's say when you go up in temperature, okay, in this way, back in the past, you increase the frequency. And so you access detectors at higher frequencies. Okay, I have still 5 minutes, or... Okay, and now let's go back, so after this introduction, to let's see what we can say of generic of these kind of sources in the early universe. And then what we do is that we go back to our master equation, in which now we put a source here. I mean, we have seen the solution of the homogeneous equation over horizon, into the horizon, freely propagating, sub-Hubble modes, etc. Now let's put a source. But what is the source? As I told you, we need tensor anisotropic stresses. Okay? Where do we go and search for tensor anisotropic stresses, given all that I told you, that meaning that where we have the right phenomenology are phase transitions. So why? The first reason is that, as I told you, phase transitions are in general driven by the change of status of a scalar field. So when this changes of state, this guy, it creates spatial gradients. And if these spatial gradients are arranged in a way that is transverse and traces, you get a source of gravitational waves. What you can also have is that this period of, in which you have the phase transition is actually moving the fluid around in the early universe, okay? And so you have bulk motion. And here this is energy density, pressure, and this is the relativistic gamma factor associated to this velocity. And if these bulk motion are chaotic, for example, if you have turbulence, they certainly in general have a transverse traceless component, and therefore they can source gravitational waves. Another thing that you have is electromagnetic fields. Okay, they for sure, the energy momentum tensor of an electromagnetic field has a transverse traceless component by construction, and so it sources gravitational waves. What you can also have is second order scalar perturbation. So these are the Bardeen potentials out of inflation, and if you go to second order, they are not homogeneous any longer, they have gradients, and so this also sources gravitational waves. Okay, so you see that there are several processes that you can look for in all these phase transitions to provide a source of gravitational waves, and all of them must be treated as random variables, as I told you before. What does it mean that they must be treated as random variables? It means that this guy here now is a random variable, and so all you know, as much as for the gravitational wave, is its two-point correlation function. Bear in mind here that for the source, we need the two-point correlation function at an equal time. Okay, so this is the anisotropic stress power spectral density taken at an equal time. Why we need it at an equal time, we will be clear in a second. And now the exercise I want to do, of course, not now, maybe we do it, we go on with this in the afternoon, is to consider, first of all, let's not go in the detail of every generation process, phase transition, inflation, etc., but let's see in a very general way what can we say about the gravitational wave signal for two limiting cases The first limiting case is a source that is fast. Okay, so it's operating for less than 1 Hubble time. So in the early universe, it means basically, this source does not feel the expansion. And this, as we will see, gives rise typically to gravitational wave backgrounds that are peaked. Okay, so the spectral density has a well-defined peak. Continuous sources, instead, means that they go on for several Hubble times in the early universe, so they do feel the expansion, and in general, they are not peaked, but they are extended spectrum over frequency. Okay, so we will see these two solutions in the most general way possible. Okay, thank you.
Thank you very much, Chiara. So maybe we leave other questions for the afternoon because we need to go to lunch, unless there is a quick one. Yes?
Thanks. So I understand we only have access to the statistical properties of this, right? And then under the assumption of Gaussianity, I guess it's also fair to say that you fully describe the signal with the two-point correlation function or whatever. So maybe this is a very naive question, but then in that sense, is it fair to say that we can fully characterize it enough that if you have like a very strong cosmological background, foreground, whatever you want to call it, in LISA, you could characterize it fully enough to subtract that and then potentially see signals less loud than that? Is that possible?
I don't think so.
Okay.
So it's not that you really can subtract. It is the same situation. In general, people ask it reverse. You see, suppose you have a foreground from astrophysics. Can you access a background that is under it? The truth is, you can never subtract it. What you can do is that you can characterize it extremely precisely. Typically, if it has a very high signal-to-noise ratio, then you can really characterize it very precise. And then if there is something that goes wrong in your characterization, so you say, okay, now this is the spectral density, this is what I expect, it is from this source, and here I see a little bump at this frequency. So what is this bump? I know that it does not come from my source. I have characterized very precisely my source. Now let's interpret this bump. In that sense, you have something that is somehow smaller, but that you can describe anyway because your main signal is very well characterized. But it's not that you subtract it from the data stream. I don't think this you can do.
Okay, thanks.
Yeah, thank you very much again. Let's reconvene at 5 this afternoon.